we'll get that to that in a second.
Good afternoon, everyone. Thank you so much for all the participants from LinkedIn, online, and also here in Omaha. I'm pleased to introduce our distinguished speaker, Dr. Simon Laflamme from Iowa State University. He will deliver an exciting seminar on 3D printing for smart resilience. Dr. Laflamme is the Waldo Wagner Professor in Civil Engineering and the Director of Research in the Department of Civil, Construction, and Environmental Engineering at Iowa State University. He holds a Court C appointment in the Department of Electrical and Computer Engineering. He received his PhD from MIT in Structures and Materials in 2011 and was awarded the Early Achievement in Research Award in 2017 and the Mid-Career Achievement in Research Award in 2022 by Iowa State University. He is also a fellow of the Institute of Physics. Dr. Laflamme's research yielded a textbook on structural motion engineering, 5 US patents, and more than 300 articles in the area of smart structures and systems, structural control, and structural health monitoring. He's a member of various editorial boards, including MSSP, Mechanical Systems and Signal Processing, Measurement Science, Technology, and Sensors. Please join me to welcome our speaker.
Well, thank you for the introduction. You oversold it. It's an exciting seminar. I'll do my best. Okay, so the talk today is about 3D printing for smart resilience. My background is in controls, mitigation of vibration in structures. So when I think of resilience, I think about adaptive behaviors. And I'm trying to think, well, how can we use 3D printing to actually empower adaptability of buildings? I've been talking to a lot of you. I think you all heard of 3D printing before. This layering process, whether it's steel, whether it's concrete. I like 3D printing because of the automation part. It's the idea that you could eventually go on site with a big truck and you just fill out the parts that you need to build the structure. Right? That's kind of a vision. It'll take a while before we get there. Unfortunately, if you look around, there's not many applications in our field in a large scale. What we've done so far, you've seen maybe houses online, 2-story, 3-story houses. There's a Walmart that was built recently that was 3D printed. The exterior, that is, masonry type. These structures are not, I mean, the parts that are manufactured using 3D printing are not quite structural. They're mostly architectural. They do have some structural demand, but nothing phenomenal. So I think we're a bit far from seeing parts that would be applied in the field that would have a lot of demand on them, like a beam for a bridge, for example. So what I'd like to do is give you my thoughts about 3D printing. State of the art, what needs to be done. So that'll be the start of the presentation. And then I'll come up with some discussion about what I'm trying to do to empower 3D printing in the field. Again, my field is feedback, controls, sensors. I'm not a materials person. I don't do that. So I will try to use 3D printing for moving forward with structural health monitoring and also adaptability of structures. If this talk can be interactive, if you want to talk about 3D printing questions, raise your hand and interrupt me, that's fine. The more you talk, less I talk, so that's good. Also, I can drink water when you ask questions, so feel free to do it. On the grand scheme of things, 3D printing is the promise, right, that we're going to have better construction, more efficient constructions, especially for individual parts. If you pour concrete, it takes a lot of people, the labor, it's labor intensive. We have labor shortage in the US. It won't get better. A lot of construction companies are actually asking, how can we tell young people, come do construction, that this is an exciting field. So we're trying to find new ways to actually reduce lead time, make things faster in the field, and of course with this whole idea that we want to be cost efficient, right? And also joint with this problem of material supply, sustainability. Can we do shapes better, utilize this materials? So that's what 3D printing could do for the user. You have a trained agent, provide you have a trained agent. So you go on site and produce the parts that you need with the exact material that you need, right? Not over pour concrete. And new topologies, for example, hollow concrete shape that would allow you to save on materials. That's what you want. will be good for individual parts, unique parts that it's hard to beat precast, it's hard to beat manufacturing process that people can do in the lab outside. The cast, right, that exists, and it's just always repeating. One good example is this bridge bearing you have on the top right. I've talked to many DOTs and I asked them, what do you have in mind with concrete and steel? What would be useful? Well, the bridge bearing came back very often. Many DOTs told me that if you could do something cool out of steel, that could be a bridge bearing, because you go on site, these are all now deteriorate like this one here that you have. But they don't have the cast anymore. Most bridge bearings are unique to a bridge. And the cast, they don't keep it in the warehouse. So if you have to replace this guy, well, you need a new cast, or you need to be able to produce it. I'm not saying you would necessarily 3D print this bearing, but to be printed a cast that could be used for casting. But essentially, that's a situation where you would make good use of a printer. So I'll talk about concrete and steel. Start with concrete here, state of the art. We're good at making concrete, start with a slurry that's concrete-like. Now we can have bigger system, like the cobalt system that you have here. They can do aggregate size up to 10 millimeters. They're trying to research 20 millimeters and going on and on and on. This is a gantry system that we call. You can also have a robotic arm that just comes and deposits. And this, you've never seen it's toothpaste, right? It's like when your toothbrushes can keep putting your toothpaste down and you come up with the shapes that you want. On challenge, you'll see that reinforcement, where to put it. I will talk about that this morning. You have to use your brain, try to figure out what is the best location you can do, given that something is coming to deposit a layer on the top of you. Right now, this wall is hollow. There's two walls next to each other, and they reinforce in between. Printing speed, you have it 3 feet per second, a meter per second. It's quite fast. It can do at least what the companies call pretty cost-effective houses. There's another video showing toothpaste rate. What's nice about this one is they show the overhang for a door. It's a 3D printed opening here. You see that we're going to 3D print over. It's good. Remove it, it makes you very simple system. Essentially, the key is that slurry. Make it portable enough, yet capable of drying fast enough. If you do 3D print concrete, what I think the low-hanging fruit is new shapes. New shapes because you want it hollow, you want to save on material. And if you get a new shape, what becomes exciting is that you can rethink the structures of tomorrow. Are we going to use a T-beam, right? Well, maybe there's better design that you can do for buildings that could be in bridges that could be more efficient. And for example, this wind turbine tower, bottom left, that's a hollow core and also hollow wall. You just put this kind of zigzag pattern or sometimes honeycomb pattern to save on material, save on CO2. Some researchers look at just for fun, trying to come up with a beam of post tension, so little parts that you put together in Legos, post tension. Some challenges, what's the benefits and challenges? Benefits, well, we don't tell you cost, CO2. For example, we have at the bottom some cost of concrete. That was 2 years ago, concrete mix versus 3D printed concrete mix. Similar cost, if not cheaper. It's fast to make, but the challenges, well, listed there, but the main one we care about is really the interlayer bonding in terms of structural engineering. That's going to be the main problem that you're going to face if you try to implement in the field. Every part you will produce will be individual. It's a new part. Right? You cannot test it, not destructively at least. Because if you do, it's gone. You have to print a new one and you have to test it. I mean, you can't just. So you have to be able to tell the client, often the DOT or the construction company, that what you produce has no certainty of performance. It will perform as designed. It won't be cracked. It won't crack. It won't. There's a truck that goes on your bridge, it will survive. That's of course right. That's what we do as structural engineer. And now, of course, this idea of reinforcement bars. A lot of people have been trying to find new ways where you can put them. But really, I think the key point to enable this concrete, pre-printed concrete to go in the field is ensuring quality of the parts. You have here, talking to students, talking about architects at Iowa State, they 3D print for fun. And you can see that they're pretty good at it, but sometimes you have a problem with the layers. This part will not survive structural loads, right? You see this little, it's hard to see, it's very small, but you have a layering problem right here at this level. Right? It kind of collapses on itself when you do it. Okay, that was a quick overview of concrete. Now here's steel. Steel, there's many ways to do that. Two that we like. One that applies to large scale, mostly if you want to do a big structure, it's going to be wire arc manufacturing. So it's a welding process that's continuous and never stops. So you just weld your part continuously, call it one. It's a fast process. If you want to make an accurate shape, this powder bed fusion is a good one. It's really slow, very expensive, but it makes really nice small parts. There's an example of one from Lincoln Electric on their website, a little video they have. So they can just make this part by welding, fairly precise. You kind of have to go back after that to do the finishes. That's a good process. This MX 3D pedestrian bridge 2021, fully 3D printed. 3 parts that were 3D printed in the lab, and they assembled on site. So a great example of what we can do in 3D printing. Personally, I think that we're closer in the field to have 3D printed steel reach structural engineering than concrete, because it's easier to guarantee quality. Although we'll see some issues with steel, but we're able to get this bridge done, right? And there's people on that bridge. Pretty cool. Also, this whole process of talking to companies and DOTs, some good example that a firm told me, SGH, they like data of connection. 2 reasons. Steel connection, well, first, can really customize to have the most perfect connection, right? From a theoretician, you'd be like, well, this is where the load is going. This is a load path. That's going to be the best connection. It will show me the load path, right? It makes you proud. But good, unless it's always the same connection, there's a repeat, and you're better off testing. In any case, the best application you could come up with is a retrofit. If you go and gut a building and to redesign it, right, to retrofit it, there will be problem connections with the walls very often. All those connections will be fairly individual. They're having issues with that, so if they could 3D print connections on site to be able to attach new beams, that could be a big time saver. So we've got benefits and challenges. Its benefits are fairly similar to one of concrete. We can also do a large component with steel. You have a little video here. Here is Rivero from UF. Nothing else has sound. So yeah, again, it's this process of welding that exists. We're able to make years with that. So it works well. Same process of CO2 emission reduction. With this process requires less energy to produce shape. So that's the main issue. Like concrete would be at the damage level, where if you don't control your heating process, the speed is too fast. You create some stresses, residual stresses, and thermal warping in your system. So that's, again, it's when you start layering, you have to be careful, have some feedback, and have this idea of, am I doing it well? Am I going to have problems in the future with this part? Is it going to function as designed? Right? Similar issues. Can I ensure quality? Well, let's talk about that. If we have new technology in civil engineering, we have this vertical approach. We're very, very traditional for most things. Usually a project, it's been like that for 5,000. There's somebody that wants a project for some reason. And nowadays, it's mostly to make money. So rate of investment ROI, rate of return. And once the client has a project in mind, they give it to the architect design, and the architect say, okay, give it to the engineer for sizing, for ensuring the codes are respected. Engineers give it to construction, and construction makes it. Simon comes up with this nice 3D printing process for a specific part. Well, I have to convince the owner that that person will make good return on investment, right? Life cycle analysis, for example. I have to go to the architect and say, well, these are the topologies that you integrate and what you could use to design the structure. And I go to the engineer and say, well, this is how you size it. This is the parameters that I have for the material. And after that, I have to teach a construction company how to make it. And of course, if you look at these items, they're all interrelated, right? The topology will govern sizing, will govern the life cycle analysis, and how you make it, for example. So what we have to do is rethink the way we train engineers. And that's not an easy question to answer. How do we do that, right? ABET is there, and also we don't like to change things. Here's what I propose. You'll see it's fairly easy. I'll take the first box and the last box and just put it together, make it a circular approach. So what we have to do is find a way to train the new generation of designer, architects, engineers into thinking this process as an integrated approach. So every time we have this new technology that comes in, it can be easily integrated because we'll have digital models that we'll be able to use to make, for example, lifecycle analysis, to make engineering analysis. We'll have access to what I call smart connected systems, sensor data, feedback systems to tell us how parts are performing. Advanced manufacturing machinists will need to be involved as well to tell us what can be done, what are the frontier of fabrication, what are the problems, what can we do to make fabrication better if we design something with a different topology. And of course, what talking about resilience here, right? This resilience model, lifecycle analysis all need to be included to make sure that what we design makes sense. This, coming back to that bridge here, that's the last time you see it in my presentation, but that was one of the best examples I could find of this circular approach to the design. They made the bridge, but that wasn't the end of the story. It's being monitored. It's being monitored with sensors. You have a bunch of sensors on the website. You can see, I think you can see live data still, but cameras, train gauge, measure temperature and all that. And they have a digital twin, a digital model on the side. And you look at the response, making sure that the bridge behaves as it should. Like really simple. Also a bridge block to be just bend. So you can measure, look at the people, the bridge, and is the bending moment making sense? Just that. And then you ensure this bridge is behaving as it should. There's no fatigue crack that generated or problems, right? Some ideas. Fatigue crack will be the other technologies know where they are, but you see if the bridge actually deflects as it should. My vision in enabling 3D printing those parts that I would call real structural parts, not walls, is they will need to be able to give us data. To give us every single part will have embedded system, a sensing system that we're able to use along with the digital twin to know the part is functioning as designed. And that's because these parts are all individual. Just because of that, we need to be able to make sure that each part will be functioning as we want. Maybe a crazy vision, but I think it's feasible. And that's what we've been trying to work on in my lab. So this is this notion of smart resilience. Trying to deal with this idea of uncertainty in design, and uncertainty what we produce with a 3D printed component. Talk about different level of resilience, of smartness, intelligence, and resilience. First one is embedding sensors, so getting data. Low adaptability. Adaptability to the process would be mainly the engineer operator that would have access to data, investigate what needs to be done. But that'll be the bigger part of my presentation. What I'll talk about is integration of sensor through functionalization of materials, making materials capable of self-sensing. And then the next level is using 3D printing for what it is to empower buildings with adaptive behaviors. It's trying to have new shapes that we can leverage. And we've been doing that, 2 projects that started recently. I'll give you a few slides, it's mostly for market purposes, right? No, but if we start that, we don't have much data on this, but we start to look at metamaterials in buildings, adaptive metamaterials, and also multi-stable system we can use to play with facades. Let's talk a tiny bit about functionalized concrete. So smart concrete that we call self-sensing. What we do is we take concrete or any material and make it a sensor. We do that by making it a piece of electronic that often is going to be a resistor or capacitor. And the value of resistance or capacitance will change as a function of the geometry. So if that geometry changes, there's a change in the resistance path, change in the capacitance, so on and so forth. And with concrete, we like to use a resistor very often. see why very soon. But we've done some tests at the University of Perugia, Italy. We made a slab of concrete with that was able to that was a resistor, and we're able to track cracks that occur in a concrete. That's a hammer that we use to hit that slab 100 times. Measure the crack, measure the flow of the electrical flow in the slab, and then we're able to look at where the cracks could be. Again, the Italians, they like bricks because of clay bricks, historic structures. We don't have many of those that we wish to monitor in Iowa at least. But same idea, 3 smart bricks, it became a smart wall, everything is smart. But we're able to track the flow of loads through the wall. So there was a crack in the masonry, then you have a change in load path, and I can say, well, the Colosseum's about to collapse. At our state, these were done with top one carbon nanotubes, the bottom one with titanium dioxide. We use carbon black in our lab to be able to explore a large scale. Carbon black is very cheap. It's a cheap conductive powder. Find in a printer and car tires. And we just want to see if for non-destructive application, it could give us a better signal for faster investigation of concrete, especially for roads. And we did we took a beam, loaded it with a lot of carbon black to make it very conductive. And you can see the signal, the eddy current signal, of course it was better. It was a terrible beam though. You just scratch it and you just dig in it because of the carbon black. But anyway, so we did some research on this. That's a secret, so don't tell anyone. I hope it's not recorded. But how to make conductive concrete. So essentially when you have concrete that's it's a resistor, and then you keep adding conductive particles, you mix, and at some point you switch from a conductor to a resistor. Sorry, from a resistor to a conductor. I think that's right. So when you have this path here of resistivity that switches from 2 different electrical behavior, we call that electrical percolation. That percolation threshold, that S that you have, this is where you want to be when you make a sensor. If you are into that S curve, whenever you have strain in your system, the conductive particles get farther or closer very quickly, and then you move fast along that S curve. So you leverage what we call the piezoresistivity of the material. Usually, particles, pretty straightforward, conductive particles, more expensive they are, more they can conduct, but they're harder to mix. And cheaper they are, less they conduct, but easier they are to mix. Carbon black is at the end of the spectrum, easy, cheap, but you need a lot. And carbon nanotubes, very expensive, hard to disperse. And in between, you're gonna have carbon microfiber, graphite, things like that. So we started asking ourselves, can we 3D print sensors made out of conductive concrete? And that was a couple of years ago. We started to look at that. So we had a cement powder, we look at different materials. We tried to make this conductive toothpaste, right? We look at graphite and different type of carbon microfiber, milled and chopped. Look at these together and mix them. And I don't get too much into the details. Essentially, this is how we make it. It's like making a cake, all the dry ingredients together, mix it, then we add water, and that makes our slurry. The challenge is to find the right amount of water when you print to make sure that you can 3D print indeed, that you don't have slumping of the material, and also you have a good interlayer bonding. And you have a little video here of early trials.
Maybe. This is the last layer in the west of automatic.
So similar to what you've seen, as you said, we can deposit without having much issue. Now what you have is copper mesh you see in between. This is what we need to connect to the sensor. We have to take measurement. So with the presence, you see something that is much more visually appealing as we move forward with this presentation. Here, we'll try different mixes. That's all you do when you look at the percolation. So you try different amount of graphite, different amount of microfibers, and try to plot this S curve to know where you can be in that percolation threshold. Just look here at the geometry that we have. So we try to keep those mesh constants. What we measure is the strain between both mesh. We connect to both, and that's your resistor. You measure resistance, and that resistance will change as a function of strain, and hopefully you achieve some good sensitivity. A big question I get a lot of time for people like NDE is how do you make sure that your carbon or microfiber are well dispersed, especially if you're using nanotubes? You're not sure. In our case, what we do is we load the sensor with current. It heats up, and we look at the thermal dispersion as a function of time. So if your particles are well dispersed, you have this nice distribution of heat as you go up to here. If it's not well dispersed, you have this accumulation of heat at some level. So for every block we have to make sure it's well dispersed. If it's not, it's like that, we stretch it and ask the student to make more, but usually they make more than 3 samples to make sure that we have 3 samples that work well. Typical test that you will do if you try to make sensors on the concrete, you just press on it, actually. And you take measurements, you have a video with how it's done, we just apply different quasi-static loads on it, sometimes dynamic to look at dynamic performance. And we look on the left as the applied load, on the right is the measure resistance. You can see that it follows the load, and that's fantastic. So we look at these data and try to establish which one's the most sensitive to strain, and that will give us our percolation. So this is what we're after. Try to see if we do have this electrical percolation that exists in sensors that stamp, right? Once you print them, if they're still holding up, can we achieve percolation? This is not a log plot, so you don't have an S curve, but with a log version, you can see there's like an S type transition. So where sensor need to be done in that little area. So we did it, it works. Also did some strength tests. Some people would wonder, are you making your sensor weaker than actual paste? And no, because of the carbon microfiber. We did increase the Young's modulus, but it's not a discussion about materials. It's a discussion about sensing. So we move forward now, trying to avoid questions about materials. Resistance versus strain. I might have chopped off the x-axis here. The slope of that curve is the sensitivity. We call it gauge factor in sensing. Typical gauge factor for a sensor is 2. What we achieve here is 665. So quite improved, right? So we have a sensor that's very sensitive to strain. Dynamic data can see that we can follow the dynamic load. I mean, there's some discrepancies, but that's a good sensor. Okay, so that's the story. We made toothpaste that works. We're good. But now we want to integrate it to the printing process, right? That's the main challenge. So we tried to, the next step was to embed it in concrete. So concrete and a cementitious sensor. So we've taken the traditional method to do it, a cast. We cast half of the beam, we 3D print a layer, and then cast the other half. And that's our embedded sensor that we have. Then data. What do we have here? Well, a lot of data. They all work. We look at different patterns, different number of strips, zigzag patterns for fun. Theoretically, the number of zigzag patterns you have in the sensor shouldn't matter at all in terms of sensing. It's for other reasons, for heat dissipation, that we do that. But we try to see, if you've seen strain gauges, they have these zigzag patterns, and then we try to just say, hey, we can do that out of concrete. It's more visually appealing. But you have the dynamic sensing, we're doing fairly well here, right? We can follow the pattern that we have in terms of sensing. So that was the other demonstration. These beams were very small. So now we try to go a little bit bigger and also more towards field applications, something that makes more sense. So we did what we call smart beams. Where the first layer, we have a layer that is conductive, a layer that is not. And you'll see in the video that we put reinforcement as well. Not just because we want to, just because we want to demonstrate that we can 3D print with reinforcement. And also, well, for testing, once you start cracking it, you don't want it to be destroyed. That's useful. So this video is 1 minute and 30 seconds. So some good music and follow this music. All right. Enjoy. This is what I force my students to do. So you have the conductive particles. Water. the best way to this hybrid printing? Which is especially just put a sensing language. Electrodes that are connected. These are bars. These are samples that are just back. There it is. Electrodes. So they use that slide. It will work well. So I'm trying to put that into a drawn paper at this stage. At the next stage, we investigated recently, can we do a larger scale, mid-scale. This is a 3 feet long beam, 1 meter. And try to repeat that. Also take that a step further, not just print a smart beam and see how well it behaves in terms of strain, but can we take measurements while we print? Would that be useful? And we did. No videos here, sadly, but that's the view of the conductive part. They were printed with reinforcement bars with the electrodes here and then the top. Resistance as a function of time. You can see, you see my cursor? No. I mean, that's no reason. So you can see the time series, right? Every time it's a new layer, there's that jump. That jump reduces because now we're measuring strain along this horizontal axis, vertical. So it's just a compression of the concrete that gives you that. And I soon had time to look at the digital model they created to see what sort of resistance we should have if every time we have a new layer, there's no damage. And he was able to fit the electrical data. So that was a good indication that could work. So that's coming up. So the next few steps. Also did a quick investigation on damages. That's the obvious case, but I want to make sure they worked. These are back to the smaller beam, the smart beam video. That size about a foot. And I don't know why they made damage. I think they just, with their finger or something, they just make some discontinuity in the printing process just to investigate. Nothing you would publish in the papers. I told them we have to repeat that, but with a formal way to introduce damage. You can see this obvious where whenever there's damage, there's a different path in your resistance time series, right? It's no more this nice little step down that you have. Same thing for this other type of damage on the right-hand side, whatever that is. You have this discontinuity in that resistance path that you were expecting. So there's promise there. The question we wanted to ask is, can that track very sensitive damage like interlayer bonding? I don't know yet, but we'll investigate that. Maybe I come back in 20 years and I'll tell you. So we do a lot of work with the University of Perugia on that, so I got to go there every year. So these are my kids. They get to come. They love that bear, those bubbles. It's a 1 year apart each. Yeah. I went from last year too. So Perugia, if you don't know it, it's Perugia, the province of Perugia, capital is Perugia. It's like the Iowa of Italy. It's right in the middle. So a lot of meats. Go there. It's nice. Wine. Okay, enough. There's no more fun stuff in my presentation. Now we're back to research. Okay, I'm going to tell you more. So we're done with concrete. Now, how do we empower the utilization of 3D printing, smart resilience, through what 3D printing really is? So this capability to make different shapes that we're not able to use through normal manufacturing processes. So metamaterials it's not a new type of material. It's simply different topologies. So it's a shape that you rethink to a different shape to be able to give it extra different properties, whether it's acoustic, mechanical. Where we deal with in my lab is the stiffness damping control to mechanical. Sorry, it's just like my brain went somewhere else. For about that samples here, 3D printing steel. Because that's simple with this little beam to that. It's coming. I'll circulate that around. So we 3D printed that in my lab. We're trying to 3D print steel for students. There's that WAM or SS process. These are very expensive. What we do in my lab is filament deposition, like you would have in any small bamboo printer at home. What that is, it's a polymer that has particles in it. steel particles or bronze. You melt it, make your shape, but then you have to sinter it. So melt the part so that all the polymer burns off and still melt just enough to create contact, create your shape. So we did steel and we did bronze. We see the bronze one has some issues with the sintering process, but we're trying to get there. So hopefully the students will be able to do this. Yeah. Hopefully our undergrads will be able to play around with the printer because it's cheap. Okay, back to metamaterials. We're trying to rethink shape to make supplemental damping structures, essentially. So we look at different topologies. This is one of those beams, and I'll pass it around. You can see there's a lot of deformation in this. But when you deform it, you can see the opening, right? The little walls start to exert friction on each other. One shape that we like to do that is a Carroll shape that you have. Mostly all those 7 shapes here. There's a lot of little walls that exist and a lot of friction they can create. So we investigated these different shapes to see how much friction do we get versus stiffness. So how much damping versus stiffness. We also look at different other shapes. I have undergrads that work on a project and they're like, oh, let's try a new shape just for fun. And I will spoil the suspense. The shape that will win is this one here, the Carroll hexagonal shape. So very interesting that an undergrad is able to mess around with stuff. The vibrating beam. This one is a defect, right? We didn't use it. One of the surfaces welded together, like the printing part. We had to like shave it off.
So it's the last one will be fun, right?
Yeah, this one will win the game. Yeah. This project just started in September. So we have a few good results, but yeah, it's gonna stop there. I'll do the next few steps. But we've done, we printed a bunch of beams. And we look at their stiffness versus loss factor, so the capability to dampen. One thing you can see that is very problematic is the stiffness. So the first bar that you have is a control beam, normal beam, 3D printed. The plane stiffness is really high. It goes up to 196 Newton, whatever it is, 196 something. Compared to those guys that gave us the better stiffness, that will go up only to 60. So 10% of the stiffness. Metamaterials for damping, they will move a lot. You need motion to dampen. That's one of the secrets too. But this stiffness is not acceptable. I'll go somewhere with that. You can see it's big stiffness here, big loss factors, so good shapes to be able to dissipate. It's load dependent with those metamaterials because more load, more displacement, more friction you get. There's more load connection to the loads, more friction on surfaces. This is another challenge too. If you are to try to design a beam or a column or some parts in the building that dissipates energy, the challenge is that you need to be able to control it as well, right? You cannot just say, put a shape there and say, I hope it's going to work. And now we look at this table. This is a summary of those results. We're like, okay, that's fine. There's some promise to it. Some shapes are better than others in terms of energy dissipation and stiffness, especially those 3 shapes. There's the one or two that won the game or will win the game very soon. We're able to get much better energy dissipation, 12.3% compared to a control beam, but the stiffness is abysmal. I'll tell you about smart resilience, right? Not just passive weight. So we want to be able to adapt. So the next step was to be able to control the stiffness of this beam. So what we've done is we passed through rods, not this one, but we made hole, friction rod through, and with the capability to post stress. So with nuts, they can just squeeze at the end. You have a little schematic here. And more you squeeze, more post tension you have, more stiffness you have. Now it's time to have a trade-off between stiffness and energy dissipation. So, yeah. So you can say, oh, it's like normal time, I'm gonna have stiffness. There's a hurricane, a little earthquake, I can just unload. You can see here, low displacement, different level of twisting. Here, a lot of energy dissipation, low stiffness is the slope, so low stiffness. And as you can really boost like this turns that you put on those nuts, the post tension, you have a lot of stiffness. I will skip this slide. The next slide is a summary of all of it. You have here with 3 different shapes, this beautiful trade-off, especially in red here, energy dissipation versus stiffness as a function of post stress. So you can really choose how much you can manipulate, right, when you do that. So that's the next step. This stiffness that we reach is up close to 100, right? Went from 16 to 100 Newton per millimeters. Doesn't matter, 100 versus 196. So we're getting much closer. So we show that we can do it. And now the next step in research is really trying to understand why we have that. So trying to come up with different models. So that's back to simulation. Once we have this better understanding, we'll be able to go back and have better shapes to do this. You have the beam here in action. It's just bending. So we tested. And you have the rods here, the schematic as well. Okay, well, be patient with me. This is the last sub-project too. The next step we're evaluating this one. It started in January. It's a climate project where we try to look at facades of buildings. And can we use 3D printing to come up with new mechanisms to move the facades around? We're looking at bi-stability. So a system that can reach different state depending on motion and remain in that state once it's reached. A light switch will be one of those systems. If you press hard enough, the switch goes in a different state, but will stay there if you don't touch it. So we've been working on that. The main idea is that some buildings have what we call a rain screen system. Top view, you have the rain screen system and an air gap with connection. So we're trying to leverage this air gap to be able to put devices to rethink the way we can use the facades. Being a control guy, my main intention was to use facade for inertia to be able to dissipate energy. As the cookie crumbled, it became a project about energy efficiency for building. Fine, I still get my way with connection. And we do work with an architect on this, 2 architects. A lot of adaptive facades that exist in the world. Usually use a hinge with an actuator, maintain a position in place. And our argument is that you can do bistable, multi-stable system. You can reach those states in a more energy efficient manner, much more energy efficient. You have another example of facade here, Cal State. This one is adaptive using thermal energy. So those little elements will heat up. They're designed to heat up and close when there's enough sun. Cool stuff. It started with me trying to dissipate energy. So what we tried to do is come up with a connection that would be stiff enough. Once you displace it, at some point it snaps into a different regime and starts to vibrate. You can dissipate vibration. So you can see in the graph here, this little scissor jack, very simple system, just a proof of concept. We've done that with Lehigh. So you start pressing it, you have a normal stiffness system. At some point you press hard enough that you just snap it and it goes into this other regime. So you can really, in this force displacement loop that you have here, start spinning a lot of energy really fast. So it works well. Sadly, there's no video on this slide. But then came up with the climate project we want to go after, and we start to explore those mechanisms. And we come up with this shrimp. So this is my first time playing with AI for making figures. We talk about pictures. The shrimp. We were meeting at Iowa State, so it's 3 teams. It's Iowa State, St. Thomas, and Florida, University of Florida. We were having collaboration week, so we need a logo. So I asked ChatGPT to make an angry shrimp. It did that, and we all liked it. And I also said, well, it has to have Iowa State colors, St. Thomas, and Florida. And people in Florida is like, where are we just this? Well, I don't know, it's AI, just do it. Anyway, we tried to look at those surfaces and mechanisms that could actually move and clamp or snap into other positions. So we look at walls. It's pretty architectural. A wall of flower pot that we can just actuate to be able to let the light come in or not. And we also want to manipulate this wall to get it closer to the structure or not. These are all hinges, so very little problem with fatigue if you do that. And the thing is, on paper, those bistable systems are very, seem attractive and easy to do, but once you start to 3D print them or produce them, it's not the same thing at all, especially one bigger. So as we kept exploring, want something a little bit more attractive, right? Something that will be easier to manipulate. We came up with those buckling beams for the surface. Like this one is 4 different states, cornerable times, whatever combination you can have. We can see that we can achieve different states of that surface. Okay. And then the shrimp became this recently. We're about to go test at the University of St. Thomas. what we produce is this little guy here with different three times 4, 12 different buckling elements in it to try to see how well we can actually reach that space for the surface. We try to reach that three-dimensional space. It starts flat, and can we do something that just reach right hand side, left hand side, everything full on itself. So we're trying to come up with this design. You have it here. My son trying to snap it. There you go. Different state. Pretty cool, right? This is a picture, and we're trying to make it more rectangular to be more consistent with building shapes. You see. This one worked, but we're sticking with this one. So we printed a bunch of these little guys. We have a test ring to actually look at the actuation versus displacement versus how much you reach the space to be able to quantify and then understand that mechanism. To eventually make a system of system. We're not there yet, but it's coming. That was the last slide. Yeah. Thank you to sponsors. No conclusion slides. Short enough, right? Thank you.
So much. I think this was so exciting. Hope everyone enjoyed. We have time for questions from audience.
How do this sensor like connected to monitor and programs?
In the concrete?
Yeah.
Well, so it's in the lab, so we have a device that an LCR meter that can measure resistance, and we just connect the measure resistance and log it in LabVIEW. Yeah.
Is that like straightforward to program?
For strain, actually, measuring strain is really easy. There's many devices that work on resistance. So you measure voltage, essentially when you do that. But quite recently, measure voltage. The harder part is you make sensors or capacitors. That's it more. It's difficult to measure capacitance because of the antenna effect that you have. But otherwise, resistance is very common.
So they're like the labs, the lab, not like outside.
Oh, and outside you could. This is something that really easy to either buy or develop. These connectors that we've made are kind of screw holes. So our vision is that you just put screws in to plug the holes to make it architecturally okay. If you go inside, you remove the screw, plug in your machine, collect data, unconnect, and leave.
So they're kind of portable?
It would need to be. You cannot have that constraints because, well, most of the work we do with the Italians, they have a lot of funding because they're working on historic structures. You cannot have cables in historic structures, right? Unless not permanently. So this cannot be a structural automation system-based concepts. In our case, well, that depends on the shape. I mean, if it's a hollow shape, you can always find ways to hide. Frankly, it really depends on the application. I didn't spend much thought there. I just assume it's something that if you want continuous in the structure, it's possible. Because we do it on bridges. There are bridges with hundreds of string gauges underneath. You've never seen it, right? But there are a lot of cables. They're not all wireless. It's all the cables that go to a computer on site. So 200 cables for 100 sensors. And you have this mass underneath. And then the computer transmits wires. But you don't see it. It's hidden. Yeah. So I think we can do that, but it'll probably depend on the application.
Is there a way to make reinforced concrete structure with sort of like making for the complicated like structures and rebars? And
you mean 3D print the rebar as well?
Yeah.
Yeah, I think some people have been trying to research it. Carbon micro CFRP, carbon fiber polymer. Carbon fiber reinforced polymer. Yeah. The problem is their printing speed is different. The concrete is really fast. CFRP is really slow. Steel even slower. All things relative. But I think some people have been trying to come up with new ways, or for example, spitting some steel ball you just quickly weld together to go faster. That's one way. It's not quite the field of interest that I have, so I didn't spend much time looking at this. But I know some colleagues have been definitely looking at that, or just even like having robots that come and place the rebar while the process is happening. The problem is replacing it in the slurry, in line with the slurry, because you do displace it, and then you can create some structural issue while you do that instead of forcing it. And the question also is it bound well with that slurry? Yep.
Yeah, you said no material question, but no material question.
No, that's not allowed.
I actually want to follow up with what Mina asked about the rebound, because in the last few years, we reviewed quite a few NSF proposals. And like what you mentioned, there are several different approaches. My opinion, none of them really work so far. But I want to ask you, like, not actually still, but I mean, you present some very unique concept of like damping system and metamaterial. But I want to ask you your opinion about a multi-material system. Whatever way, I mean, again, like the question Mina asked about putting rebar in, I haven't seen any way that it works so far. So, but apparently you use fairly different approach. But one of the reason I asked is the reason we have steel and reinforced concrete because of very different technical. But does not need to be like that. And one thing I always feel that 3D printing, we have to jump out of the box of whatever we have because we can print very different way. You show us the very unique way. So I just want to hear the general feel about like how do we need to incorporate another material? If yes, what's your sort of?
Good question. It's hard to answer. I think you nailed it by saying it has to be about rethinking, right? What we do outside the box. I agree that it's hard to sell a structural member without reinforcement, or even with different mix and you claim will be strong enough. We push the limits of our stuff with ultra high performance concrete that became a sensor. But even UHPC, you wouldn't use it purely as itself, as a beam for a bridge, right? The colleague I mentioned earlier, Iris Rivero at UF, work a lot together on this. She's an advanced manufacturing person. And she's trying to develop hybrid manufacturing capabilities. She said she's trying to think of ways to actually have 3D printed steel that will go along with the concrete. Hasn't started yet. They bought the printer. They have this cool the gantry system, full size. They bought that, yes, they can make a house now. But the problem is, once you have that, how do you actually have this capability to come and have a robotic arm that would 3D print the steel? But yeah, I didn't spend much time in that era of materials myself because I really focus on the same arguments that somebody like you come in and say, I have this material that's super strong. I'm ready. I have my sensor, and I'll tell you if it's functioning as designed. And then if you sell it to DOT for like capacity X, I'll tell you what is a real capacity. Hopefully it matches, right? But I have no further wisdom, I guess, on how that could be done to replace the postman other than being in doing it. I don't think anybody's going to buy it. There's no steel at this stage.
Maybe just forget about it.
Yeah, where it could actually be useful, right? Where people have been trying to make houses or quick construction for disaster relief. That's something that would be acceptable, especially if you're not sure about this trend, but we'll be good for 2 to 5 years. That could be one thing. But yeah, to the point of building except I'll always give it that T-beam for a bridge, we're very, very far from that. We've never achieved that. But still, I think that's close. I think you see that bridge that was done. I think that's feasible.
We looked at like the long-term performance of these materials over like a year or two. Just like when I look at the 3D printed metals, like I see like there's some voids, right? That might lead to, for example, later on corrosions if we have them in the structures. So how do you reduce that, like those type of voids in the 3D printing?
Yeah, I don't know. I don't look much into the performance of metals over the long term, but because we don't have many applications of old in civil engineering or steel. The concrete's been around for quite a few years, and the first houses we printed all destroyed now because they started cracking. And the company that made them said, well, that's fine, our mix is better now, so they reprint. They reprinted the houses. I mean, they seem to be okay now, but that's the thing, right? It's like, that's the test of time. They did it. There's people that bought those houses, and we'll see how long they'll survive, or the house will survive. But yeah, that's, I haven't heard anything back, but yeah, what we did at the beginning did not survive. Because reinforcement will see, right? Because they are, I keep saying they're not too structural, but they are a bit structural. Gravity, a bit of wood, just that is enough sometimes.
Because I did notice that in the lab that you have the picture of the wall that's being drawn with 2 layers of concrete that is zigzagging between. The reinforcement is being placed only horizontal, right?
Yeah.
You're not placing anything along that goes through the layers.
That wasn't my goal. The reinforcement is not even designed. I mean, we just want to place it. So the video I've made, the interest was to get companies interested in supporting an undergraduate program.
Yeah.
It was educational mostly. Say, hey, we could do that. Start training engineers. We start taking that circular approach is something that I care a lot about. It's really hard though to get companies involved. I mean, I think it's support morally, but to the point of like trying to be a bit more involved either financially or through ideas, they're spending right now. It's a bad economy for them too, so they don't want to be involved.
You think, sure. You think that placing the rebar vertically could ruin the 3D printing process?
I don't know for a fact. Because it depends when you put it too. I'm just thinking loud. I never looked into it.
I think after the layers, before the concrete become dry, you can put your steel.
The layer is too dry.
It's too dry, it's not gonna bond, but
Yeah, I know, but like once you finished, you can try.
These are things that it's a bit out of my specialty, but obviously it's an integrated system. One should know about that. Yeah, we didn't look at that at all. I've never seen someone do it.
yeah, because that's where you're gonna have your most problems between the layers, right? And you would want the steel to be there between them.
So between layers, strategies I've seen is using microfibers and pushing them with a shear on the nozzle down, and even aligning them with magnets to be able to punch through a little bit, or having them at least vertical.
That way you'll give you that shear forces in between the layers.
Yeah, that's the best I've seen so far. I don't recall any of the results though. I mean, I bet it worked, otherwise we can't publish about it. Yeah, that's the best one I've seen. It's really using the layer itself, but then you find ways to align that. Usually they're just dispersed horizontally because of the way it comes.
Because the way it's, yeah.
So you need a special nozzle to do that.
Even I think in UHPC, when you post, even if it has fibers in it, when you pour it, the fiber doesn't always show out the surface. It's always in between the mix. It's not showing out. So if there was a way to get it to come out and then have the other layer come across it, bond to it.
Well, see, maybe it should be your field. It's about thinking. So it's just think of wild ways and don't let people tell you no, it won't work. Try it. And this is why I like to work with undergrads on the project. They have wild ideas, and as a matter of fact, that intermaterial shape you have there, that an undergrad that came up with it, I have no idea how. I asked him and he changed the topic. So
ChatGPT.
I'll be very impressed by ChatGPT. Extrapolation. Yeah.
And also, how do you think this will affect in terms of if it does become something that's the design codes in terms of design, steel design, and concrete design?
Yeah, that's something we talk a lot about. That circular approach is it's about getting the right stakeholders involved to be able to change the code. And changing the code is the thing I don't want to touch. Some researchers love that stuff. It's a lot of testing to be able to come up with solutions. But the codes, when I was talking to those people, in my opinion, the codes will need to integrate this notion of sensing. Or not the circuit direction. We will need to be able to just do that very often, get data, find ways to make sure that parts of functioning as designed. I don't think we'll be able to. And codes will need to be developed to integrate structural health monitoring solution. That's my wild vision. Any practitioner will tell you, no, we can't, traditional, but we'll need to find ways to do that because you cannot again guarantee that every single individual part is working.
You're right at the time. Let's thank our speaker for the great presentation.